Hello students, in this video we'll see rank nullity theorem. The statement is, let V and W be two vector spaces over the same field F and T maps from V to W be a linear transformation. If V is finite dimensional, then dimension of V is equal to rank of T plus nullity of T. Let dimension of V be n, so that dimension of n of t can be taken as a k, so that v1 v2 etc vk is a basis for null space of t. Then v1 v2 etc vk is linearly independent. As this v1 v2 etc vk forms a basis, these vectors are linearly independent, and we can expand these k vectors to n vectors of v, and we shall claim that t of vk plus 1 comma t of vk plus 2 etc t of vn is a basis for range space of t. Now since v is of a dimension n, it has n vectors as a basis, we can find a range space of a t, and it can be formed by span of t of v1 etc t of vk etc t of vn. But v1 v2 etc vk belong to null space of t. Since it belong to null space, transformation up to k vectors will be mapped to 0, so that these can be removed, and the remaining vk plus 1 vk plus 2 etc these transformation images will span this r of t. So span of r of t is nothing but s, span of s. So we can take that as 1. Now we shall prove that S is linearly independent set. Let the coefficient bk plus 1 into t of bk plus 1 plus bk plus 2 into t of bk plus 2 plus etc bn t of vn equal to 0. From this, since t is a linear transformation, we can take this bk plus 1, bk plus 2, all these coefficients inside this transformation, so that t is linear. We can take common t, and then t of something expression equal to 0 means this belong to null space of t, which means bk plus 1 vk plus 1 plus bk plus 2 vk plus 2 plus etc bn vn that belong to null space of t. As in the previous line, the transformation is equal to 0. Since v1 v2 etc vk is a basis for n of t, we can write that basis is equal to already the existing basis b1 v1 plus b2 v2 etc bk vk. From this we rewrite and make it as like a minus b1 v1 minus b2 v2 plus etc minus bk vk plus etc bn vn equal to 0. So when this is equal to 0, we can call all the coefficients as a 0, as v1 v2 etc vn are basis. So we can get a conclusion like S is linearly independent. So from 1 and 2, we'll get S as a basis for R of t. So dimension of R of t is equal to n minus k. Since k we have taken dimension of null space of t, and n as a dimension of v, we can rewrite the statement as dimension of range space of t plus dimension of null space of t is equal to dimension of v, or dimension of v equal to rank of t plus nullity of t. Thank you.